very pleased to be with you. Good morning, buenos dias, in Basque, I forgot to ask.
Everyone.
Oh, yeah. Okay, so to be thank Pedro for this double invitation. Yesterday with younger people, I guess, and today with two different dress codes. I understand. So my talk today will be on a new emerging direction in spintronics, spin-orbitronics. So spintronics based or not on using the classical exchange interaction, but the spin-orbit interaction. That is this relativity correction to the quantum mechanics that is very important for EV atoms. We see some result with platinum here. So, but so the main part of the talk will be on spin-orbitronics, but for those who are not familiar with spintronics, I will begin with a short introduction on spintronics. The other can sleep during this time. So you see the overview, introduction from spintronics, and then spin-orbitronics. I can say that spintronics use the influence of the orientation of the spin of the conduction electron on the electrical transport in magnetic materials, typically in a magnetic material like cobalt or iron. You have this section splitting on the band for the two spin directions, spin up, spin down. And due to this splitting, you have a different conduction property for the spin up and spin down, two channels. In first approximation, independent channel for the conduction, and in some systems with a strong contrast between the two channels, especially when one put into the metal, cobalt, an impurity having a strongly spin-dependent scattering cross-section. For example, in terms of quantum mechanics, if you have resonance scattering in one of the channels due to the spin splitting of the levels of the impurity, and non-resonance scattering in the other channel, for example, you can see below the resistivity induced by 1% of this impurity into nickel. You can see, for example, you put cobalt into nickel, the electrical resistivity is 10 times larger in the channel. So the channel is more or less does not conduct, and the conduction is by the other channel. And this is, we have the opposite effect for example, chromium impurity. There is a strong resonance scattering in the channel for chromium. So these results are not very new. They were in my PhD a long time ago, 70. And at this time, we had also some results anticipating more or less giant magnetoresistance. That is, results on alloys where I was putting at the same time, say, for example, cobalt and chromium. And then putting cobalt and chromium means that the electrons are strongly slowed down in both channels, and the experimental result was that the resistivity when these two opposite impurity, the resistivity was observed to be very high. And so this is more or less the concept of the GMR. One puts on the road of the electron not impurity, but a magnetic layer. So this magnetic layer, for example, is supposed to stop more or less the electron in the channel, and there is, on the contrary, free conduction in the other channel. And then suppose one puts two magnetic layers separated by a copper layer, and with opposite magnetization for these two. That means that this one will slow down the electron in the channel, the other there will be the current will be blocked, more or less blocked in both channels by one or by the other, and the resistivity is very high. But now is enough to apply a magnetic field to align the magnetization in the same direction, and then, of course, this channel is blocked, but this one is free, and the resistivity drops. And so there is an analogy with the kind of situation of with polarizer and analyzer in optics. And in fact, it works not only in this situation where the current is perpendicular with the layer, but also in the simplest experimental situation where the current is along the layers, because of course the direction, the electrons have these zigzag propagations. But of course, at this time in 70, I knew also that this situation is possible, this concept can work if the distance between the two impurities is smaller than the what is called the mean free path, which is magnetic if the layer of copper is thinner than a few nanometers. This is a few nanometers, this is the mean free path in metallic films. And at this time, it was not possible to prepare multilayer with that thin layer. And so I have to put this idea on the ice. And of course, in the beginning of the 80s, the beginning of microelectronics allows to introduce new technologies, like, for example, molecular epitaxy, that makes that it was now possible to prepare very thin layer and good multi-layers. And so what was done by Peter Grunberg in Germany or by my group in Orsay. And this led to the discovery of the GMR. This is our result. Applying magnetic field, we see various multi-layer ion with chromium, and the best effects are obtained for a thickness of chromium smaller than 1 nanometer. This is a condition. The thickness must be much shorter than the mean free path, and the effect is that we call giant magnetoresistance. By applying a field and aligning the magnetization, there is this drop. The effect is large, 80%. And we call this effect giant magnetoresistance, this drop induced by a magnetic field. And so you know this. One of the main applications, economically the most important, was the application to the read heads of the hard disk. On the hard disk, the information is stored on these tracks here. And the information is coded by magnetic domains today with the magnetization up or down. And of course, the density of information can be very large if these domains are very small. And then the problem is to detect the very small and very local fields generated by these magnetic bits. And today, it is done efficiently by using the JMR of the magnetic layer. When this magnetic layer, say 2 magnetic layers separated by copper, between these 2 magnetic shields are just above one of the magnetic bits. The magnetic field aligns the magnetization. There is a change of the magnetization of the resistance, and one can detect. And with the sensitivity of the GMR, it has been possible to detect smaller fields, so to detect smaller bits, and to increase the number of bits in the disk by more or less 3 orders of magnitude. So I tried to be fast because the path is not so interesting. This also was the kickoff of spintronics, that is research on several different effects, also exploiting the spin of the electrons in transport. Okay, the application also, one of the effects was that the extension of the technology of the hard disk from the computer only to mobile electronics, so iPods and so on, because it's now possible to put a lot of information on very small disks. So the development of spintronics, many other effects have been found in the intense research that had been triggered by the discovery of the GMR. One example of effect similar to the GMR is the TMR, more or less again 2 magnetic layers, but now separated by an insular layer, and the transport from the top and the bottom is now by tunneling across the tunnel barrier. This is the best layer, the best magnetic technology we know today with a insulation layer barrier of MgO. And example of a new application that is the MRAMs. You know, in your disk you have a massive memory, but the disadvantage of the disk is that I suppose the microphone works. Yeah? Yeah? Is okay? Yeah, it works. Yeah. The disadvantage of the hard disk, the memory is huge, but what is the disadvantage is one needs a long time to access to the information. 1 millisecond, which is too long for the speed of the computer today. And so the idea of the MRAMs launched commercially by Motorola in 2007 is to replace the and so now so when you switch on your computer, you transfer a part of the memory of the disk into the RAM, random access memory, semiconductor based, with an access time of the order of the nanosecond. That is what is required for the speed of the computer today. But the disadvantage of the RAM is that they are volatile. That is, you need even simply to take the memory alive. You have to inject electrical power. And so this is one of the main sources of energy consumption in the computer. You need always some electrical power to maintain the memory alive. And the idea of the MRAM is to replace the memory cells, the semiconductor base of the RAM, by magnetic tunnel junctions that is by non-volatile memory. When once the memory is heightened, it can keep the memory a long time, like any magnetic element. And the first generation was not very performant because the switching was relatively complex by sending electrical current in these lines to induce at the crossing some magnetic field to reverse the magnetization of one of the electrodes. And so this first generation has some interesting application, but mainly for in avionics. The Airbus, for example, use this sort of memory because they are also non-sensitive to the radiation of the atmosphere. There are many applications also in spatial technology, but this memory are not performant enough for our computer. But now a stronger impact is expected from the new generation, which is certainly people say that will appear in our computer in 3 or 4 years. And there are many developments. The memory already exists fabricated by Samsung, IBM, and many other companies. And so this new type of STT RAM, spin transfer torque, have another concept for to hide the memory. In fact, they use the concept of spin transfer. What is spin transfer? Spin transfer is more or less like momentum transfer when you play balls. When you play balls, when a balls collide another one, this ball transfer a part of its momentum, linear momentum to the other ball. This is a transfer of momentum. Spin transfer is a transfer not of the linear momentum of a ball, but a transfer of the rotational momentum of an electron to a magnetic material. And that is the concept of spin transfer that is that suppose you have this magnetic tunnel junction here, and this is a reference layer. So a current going from the bottom to the top is spin polarized by the reference layer, and so it can transfer in some condition. It can transfer its quantity of spin into this layer, and transferring some quantity of spin means changing the total magnetization of this layer, and in some condition it can be used to reverse the magnetization back and forth and too high. And so this new generation, based on this very performance recent generation of magnetic junction, and this effect certainly will impact, people suppose, the next generation of computers with the advantage of a strong reduction of the energy consumption, which is increased more and more today. This is 7% of the electrical power in France. So that means more than all the jets flying in the air of France. And so there is an important challenge, this reduction. So I tried to be very short on spintronics, so people can. I don't see people already. Okay, so I continue with. Okay, there are other applications of spin transfer. In other conditions, spin transfer can be used not to switch the magnetization of the free layer, but to induce precession and finally produce alternative signal, EC signal in the radio wave frequency range. And so this is another application of spintronic, STT nano oscillator with certainly many applications soon in telecommunication. And I proceed to the main part of the talk, spin-orbitronics. So I can introduce spin-orbitronics in this way. Okay. In classical spintronic, GMR, TMR, spin transfer torque, one uses the spin polarized currents or pure spin currents are created or detected by using the exchange interaction. But now it begins to be known during the recent years that also it's possible to create or detect spin currents by using the spin-orbit interaction. And this can be used and okay, for example, this can be obtained by using the spinel effect, a spin-orbit interaction in a non-magnetic material deflects the electron or spin up and spin down in opposite direction, and this is one of the ways to generate a vertical spin polarized current, spin currents. And similar effect can be obtained also by using the spin-orbit interaction in H-bar two-dimensional gas, by using the Edelstein effects, and also by using similar coupling between the spin and momentum in the surface states of topological insulator. So there are several effects now that can be used to prepare or detect spin polarized currents, and these effects open the way to spintronic device that in which operating without magnetic materials, so without the need of a magnetic field to orientate the magnetization to tune the spin polarization of the currents, using only non-magnetic material. But anyhow, magnetic material remain essential for the function of storage information, non-volatile storage. But even for this function, spin-orbit effects can be interesting to produce new types of magnetic configurations, interesting type of magnetic configuration. And so we'll see the example of chiral domain walls induced by Dialoshinsky-Moria interaction that can be moved very, very large velocity, and we'll discuss also the structure that are called skyrmions. And we'll see also that in some experiments, it's possible to combine different types of these spin-orbit effects. For example, this is a simulation of the motion of the skyrmion induced by the spinel effect in a magnetic track. And so I will discuss all these different types of spin-orbit effects composing what I call spin-orbitronics. Maybe to begin with something very simple, I will begin with an example of two examples of typical effect of spin-orbit obtained by spin-orbit interaction. Skew scattering, one of the mechanisms that of the spinel effect. It's very simple to explain. If you have the scattering of an electron by an impurity with having a large spin-orbit coupling, a large term LS. Due to this spin-orbit coupling for this one of the spin direction, the scattering potential will be more the same for electrons going around the impurity clockwise or anti-clockwise, and this, of course, will lead to a different scattering to the left and to the right, on this figure to the left, and of course the effect is opposite for the opposite spin direction. So there is a typical spin-orbit effect, and we'll see there are many other, sometimes more complex spin-orbit effects. For example, we'll see in other conditions, if we have, for example, an interface between a magnetic material and a material with large spin-orbit coupling, there will be also some configuration, not a conduction electron and a single impurity, but say conduction electrons interacting with this triangle, two magnetic atoms and a spin-orbit atoms, and then this we'll see that it corresponds to Dieloshensky-Moore interaction at the origin of the skyrmion and so on. So now I'll go into the details. I begin with the magnetic skyrmions. Magnetic skyrmions. You can see typical image of a magnetic skyrmion. This is so supposed to be these spin windings supposed to be in a magnetic layer with a vertical magnetizations. And so these magnetic windings are the main property. This is like a particle. This will be possible to move this skyrmion in the film, and the main property is they are topologically protected. You can try, but it's impossible to unwound this configuration by simply twisting the magnetization continuously to destroy this configuration and to proceed to the parallel ferromagnetic order. And so this is a concept of topological, in fact, the concept of skyrmions and of topological protection has been introduced by Mr. Skyrm long time ago for a problem of elementary particle, and it has been, the magnetic skyrmions has been discovered only 5 years ago in Munich by the group of Christian Federer. If you look more carefully to this configuration, you can see the properties. The spin are up on the edge, and are beginning to rotate anti-clockwise to become down at the center, and continue the anti-clockwise with always the same characteristic to become up on their side. So there is a rotation by 2 pi. In fact, if you also consider not only the rotation along one line, but the total rotation, this corresponds to all this orientation of the spin on the sphere. Actually, mathematically, the configuration can be characterized what is called a skyrmonic number or topological number defined mathematically this way. These skyrmions are, in most cases, are generated by Dieloshensky-Moore interaction, that is this type of antisymmetric coupling between two atomic spin S1, S2. And this Dieloshensky-Moore interaction can be found either in non-centrosymmetric material like manganese silicon or this one. You can see images by Lorentz microscopy of some of these skyrmions, in this case, the skyrmion lattice in this bulk material. And they can be found also when in thin layer deposited material with the large spin-orbit coupling, then the symmetry breaking is introduced by the interface, the absence of inversion symmetry. And this is an image, very small skyrmions. The image comes from SPSTM measurements in the group of Wyss and Danger in Munich. So it's for one monolayer of iron on iridium. So, and one of the interesting properties we'll see for application, is that this skyrmion can be moved by an electrical current. This is the first experimental result, in manganese silicons in the group, at the group of Munich. And you can see the velocity, rapidly, the velocity as a function of the current in the film, in the material. And what is amazing is compare finally the effect is a spin transfer torque effect. As for the motion of domain walls, the domain wall also can be moved by a spin transfer torque. But what is very striking is that the skyrmion can be moved by very small currents that 100 amps per centimeter square. That is 5 order of magnitude that what is needed to move domain walls in some device, spintronic device that are developed today. So this was a striking result. In fact, the slopes is not so different, maybe a little larger for skyrmion than for domain walls, but the main property, these skyrmions are very weakly pinned. The depinning current is much smaller than for domain walls. So a few words on the Dialogensky-Moria interaction after this simple picture of the main property. So this is a mathematical form. In some compound like manganese silicon, the Dialogensky-Moria vector is along the line between the two spins, and this leads with this, to this shape, vortex-like skyrmions. But for I will be mainly interested by skyrmion generated by the interface. The Dialogensky-Moria now is in the plane of the interface, and this leads to this configuration, which is like a double Néel wall. That is a rotation like that, you see, as we have seen at the beginning. And I will be mainly speak about this interface-induced skyrmions. First, because they are more interesting for applications than the skyrmion in these bulk materials that are always TC below room temperature, and also, but it brings me back to my work long time ago on the Dialogensky-Moria interaction. What I did at this time in 1980 is the problem was to explain why the magnetic anisotropy of a spin glass, like copper manganese, was strongly enhanced by the addition of a very small concentration of impurity of large spin-orbit coupling like platinum. And so the explanation that we calculate what could be the effect, and we calculate that in this situation with two magnetic spin and in the neighboring a platinum impurity with large spin-orbit coupling. In fact, the usual air-Kekulé interactions, coupling mediated by the conduction electron between the two atomic spins, this one, was also, there was an initial terms which was of Dialogensky-Moria form. And due to the spin-orbit coupling in the neighboring, and of course, due to the symmetry breaking. I suppose, of course, if this atom there is a symmetric atom on the other side, there is a total cancellation of this effect. And there was a reasonable agreement with the experimental results. And a few years later, I extended this picture to this situation of a magnetic layer on the top of a layer with strong spin-orbit coupling. And of course, we can see there are the same configurations, and that will lead to this Dialogensky-Moria vector due to the symmetry breaking, that is to the presence of a spin orbit only below and not above. And with the result that what can be expected is relatively large Dialogensky-Moria interaction, 20–30%. 30% is what has been found now by DFT calculation in the group of Stefan Blögel in Jülich. And this Dialogensky-Moria interaction induced by interface with material with large spin coupling are now known to give rise to several types of effects. For example, one of the spectacular one is this spiral structure. Of course, this Dialogensky-Moria interaction the energy is minimized by rotating the spins from the parallel configuration, clockwise or anti-clockwise, depending on the orientation of D. So this is one of the parallel configurations that have been found in the group of Wyss and Danger in Hamburg. A nice result also for a cobalt-nickel multilayer, either on iridium and platinum, is the result that this Dirichlet-Moria interaction induces a Néel configuration of the wall, and which is of clockwise or anti-clockwise depending on the substrate. Depending on iridium palladium, we have a different chirality. The Dirichlet impose some chirality to these Néel walls. Impose the Néel configuration, of course, like in the skyrmion. And the other result is this interface induces skyrmions in monolayer of iron or for not bilayer of iron and palladium. So I'll be mainly interested by this sort of, so after this introduction of skyrmions, I will discuss some general features of the interface DIME. In fact, I did a collaboration with this expert of DFT calculation, Merbeck Chief and Hongxing Yan in Grenoble. So some interesting results. Okay, so the type of calculation can be done by DFT's methods. For example, the example of platinum 3 layers, cobalt 3 layers. So the idea is simply to compare, to see the effect of, to see if there is a difference of energy between these two, these spiral configuration of different chirality, opposite chirality. And so by comparing this energy, and by identifying the results with what can be expected with this analytical expression. And of course, because there are spins in different layers, including in the first layer of platinum, what is the difference in energy give finally this, the total of this decay. Decay K being the number of the layer. So this is a way to calculate the total Dirichlet-Moria interaction. But the question that we want to answer to is, in fact, what is exactly the, how is the Dirichlet-Moria just confined to the interface or extend a little more away from the interface? Does it extend also to these spins in platinum? And so what we did in now constraining the system to have only a spiraling configuration in one of the layer, and comparing the energy, and then it's possible to isolate, to single out the decay in each layer, and you can see the result. One sees that really this interaction is really an interface interaction, is mainly the predominant term is just at the interface in the first layer of cobalt. There is some smaller, 10 times smaller in also the second and third layer, but you see even with opposite sign, and only a negligible effect on the platinum spins here. So this is one of the results. We have really an interface interaction. The second things we can look at, and this is explained in particular in this case, that in fact when adding some effects on the effect is larger for only a single cobalt layer and decrease a little, but it's not so important. What we try to see also to understand a little more the mechanism is to see by comparing, for example, the energy of these two configurations and where is located the energy, on which sites is located the energy difference. One see that to explain this large DMI in this cobalt layer, in fact, the corresponding energy, the source of the energy is in the platinum layer. In fact, the chirality of this configuration here change the spin orbit splitting in the platinum layer and change the density of energy on the platinum side. So this is something which is in agreement with this picture what I have seen. So we know a little more on this Dioulashensky-Moria interaction, and we have extended the calculation also to several systems. In fact, before beginning experiments, we want to explore and to see where to go, what are the best interfaces. In fact, the sign is different, for example, on iridium and platinum. And for example, the best system could be, for example, platinum, cobalt, iridium, because when iridium and platinum are below, they are opposite signs. But when platinum is below and iridium above, they the DMI. And what we have seen also is that one of the questions, for example, claimed by Stuart Parkin, was that it was essential to have some magnetism induced in platinum. No, in fact, we see that maximum effect is when there is zero magnetism on platinum. Okay, but I don't want to. And so, last part, on the road to applications. And so, to go to, I will present some experimental results on just platinum, cobalt, iridium multilayers. Before we started by simulation to explore more or less the way and to go where to go exactly. So we'll speak at the same time about simulations and preliminary experiments. So first, what we want to go. In fact, of course, it's very attractive to work with thin films on metals like platinum or iridium. But of course, for application, it's not realistic to work with a single layer of iron. Okay, and so what we want to do is to extend the results of this Sandanger to multi-layers to add the Dioulashensky-Moria at several interfaces of the multi-layer. For example, this system, a multi-layer system in which each layer of cobalt is between a layer of iridium and a layer of platinum. And so, because we know that opposite, when both are below, they have opposite effect. When one is below and the other above, by symmetry argument, they should add their effect. And so we want to, this is a type of sample we'll study. So why multi-layers? To have more robust system for applications, and also for some question of thermal stability. In fact, if we have only a single layer, it's better to have with a strong coupling between all the layers, to have not a skyrmion only in one layer, but to couple and to have a bigger magnetic object, less sensitive to thermal fluctuation, to have application at room temperature. First simulations. So the simulations have been performed not on multi-layer but on a single layer, and this is micromagnetic simulations. So this is the expression. So we work on a film of 2.4 nanometer of cobalt, and what one studies the nucleation of skyrmion, how they can be nucleated, and also the question of current-induced motion and pin-impaired effects. So of course, for micromagnetic simulation, we have to proceed to this form of the Dioulashensky-Moria interaction in micromagnetic simulations, where now there is a constant D, which is related to the DIG pair interaction by this expression. And first, what we want to go, what we want to study. In fact, I take an example of skyrmion in a disk of cobalt. And this is the energy. The first simulation allows us to compare the energy of the ferromagnetic state of the disk and the energy of the skyrmion state. And we are interested by this small value of D. In fact, we are interested by the situation of a metastable skyrmion here, in a stable disk or track or sample. This is and this is a range where D is too strong, and we have the skyrmion is stable in more stable than the fermenting states. So this is the best system to have moving skyrmion in a ferromagnetic layer. You can see also that one sees that when D decreases progressively, the ferromagnetic state in red compress the skyrmions to obtain very small sizes. On this side, on the contrary, the skyrmion extend more and more before breaking into several skyrmions at larger value of D. This is more or less, this is a relativistic value of D if one take all the information that we have. So it's possible to tune the size of the skyrmion. I don't want to. Nucleation. So the important point is due mainly this skyrmions, there is a topological barrier between the ferromagnetic state and the skyrmion state. And so nucleation problem is an important point. And so we try, the first simulation we try is injection using spin transfer torque and injecting a spin vertically, a vertical current with a vertical spin polarization like that, and using the classical expression of the spin transfer torque, which is this is a form m, sigma is the direction of the polarization, m is the local magnetization in the disk. This is the physics of spin transfer torque. This is what is called an anti-damping torque. It's a term of negative frictions that compete with the usual damping characterized by the coefficient alpha. So in the simulation it works. In fact, one needs small value of alpha. With cobalt, alpha is relatively large, and to have an efficient spin transfer torque is necessary to go to relatively high current density, as those used, for example, in the M-rams or spin transfer torque rams. But of course, it's also possible to use materials like cobalt, iron, boron with smaller alpha, and then it appears that it should be possible to nucleate skyrmion by this spin transfer for relatively low current density, below 10 to the 8. Actually, experiment of, okay, I can discuss the mechanism is a little complex, but okay, I will try to explain simply. So what is the mechanism, how the system can go over the topological barrier, the topological path? So I describe several steps in this. This is the initial state for the magnetization, direction red, except some tilt on the edge. And this is the density of DMI energy. So this tilt makes that there is a small negative energy on the edge. Then a current is injected and a part of the sample is reversed. It's not still a skyrmions. One can see that the rotation of the spins is clockwise and then anti-clockwise. So it is not a skyrmions, and in fact one sees that in the pseudo walls around this zone, there is a negative energy here. That is, the chirality is opposite to the DMI chirality. And here is positive, this is okay, it agrees with the DMI. And then, okay, this is like in what is called a hard bubble in the physics of bubbles developed 20 years ago. There was two walls with different chirality separated by what's called block lines. And the block lines are here. Of course, it's not the same sort of size. The skyrmions are much smaller here. And then progressively injecting a little more energy, this part of the layer here with the negative direction chimeral energy compress the part of the pseudo walls with the opposite chirality in the form of a defect, like the block point in the language of the bubble. This defect becomes smaller and smaller and suddenly explodes. And this is like the annihilation of block points in the physics of the bubble. And then the last stage is the skyrmion. So in principle, this nucleation can be done, and it exists in some experiments of this Sandanger. In fact, experiments on by injecting a current by the tip of the SPSTM microscope into a palladium ion bilayer, and you can see typical example, writing skyrmions with a current and dilating by a current with a different in other condition of field. So it's difficult to make a direct correlation between these experiments and our simulation, because here this writing and dilating is easier when for one of the spin polarization of the tip, but exists for both spin polarization. So there is a more complex effect related at the same time to the spin polarization and to the energy. And so we don't know exactly. We have to go deeper in the interpretation of these experiments. But there are other types of nucleation that can be suggested. For example, the experiments, including of Beach at MIT, but also with a Spanish co-worker in Salamanca. And by reversing, by injecting by spinel effect a current in this layer of cobalt ion, they see this intermediate state, yeah, bizarre intermediate states, and by comparing with simulation, they can see that they can reproduce these states, a state of which breaks into a deformant schema lattice. So in the simulation, they see some walls, this sort of structure with always the same chirality of the walls induced by the DMR. They introduce the DMR in the simulation, and they suggest that in fact this is due to the formation of skyrmions. So we try also this way by starting by, for example, so this is our sample. This is now our preliminary experimental result on this multi-layer platinum, cobalt, iridium multiplied by 10 to have some stability. This is equivalent at room temperature. And so after increasing the field and decreasing it, always at about zero field, more or less zero field, we see this structure. This is by X-ray microscopy at PSI in Switzerland. We see this structure. Okay, so this structure. But the question is, we don't know if these black dots are skyrmion or simply bubbles without a given chirality. The difference between a bubble and a skyrmion is that skyrmion is with always the same chirality of rotation. But if one look to the books, classical book on bubble, one sees that for the characteristic of these layers, the minimum diameter of a bubble should be 6 micron, and we have something which is something like 80, 100 nanometers. So this cannot be explained. Also, we don't see this result when there is no iridium and platinum, or if there is only also platinum and platinum both sides. And so these structures are certainly induced by DMR. They exist only if you have these spin orbit materials on both sides of cobalt, and maybe they are skyrmions. So we have, in fact, we check at the beginning. We check, in fact, we compare what can be expected with skyrmions, and in fact, the variation of the diameter of these objects can be fitted well with this value, with the skyrmion structure and this value of D. Of course, it's not a proof. It's not a final proof. It's final proof we will get certainly by looking directly to the chirality, either by MFM, but more or less by with NV center microscopy that is able to show, for example, the chirality of a domain wall. And so, for the moment, there are our preliminary results. It seems that we have some objects, and we have to prove now that these objects, apparently, they cannot be simple bubbles. They are something else. They are induced by DMR. we have simply to demonstrate there are skyrmions and then use them. And use them, what can be done with this skyrmion? For example, the motion of skyrmion, I come back to the simulations, by in-plane currents or vertical currents. In-plane currents is okay, I summarize the result. In-plane currents works, but it's not very efficient. It's not, the velocity is not larger than the velocity of the movements. This is an example of simulation. So I will not discuss this result for in-plane currents. But the best results are obtained by moving the skyrmion by the spin-Hall effect. Another spin-orbit effect. You see spin-Hall effect with the current in this spin-orbit layer. Of course, there is a strong deflection. Generally, this deflection induces a spin accumulation on the surface. But if there is a magnetic material, this spin accumulation diffuse, and this is the mechanism that we simulate. So the injection of a vertical current, and it works. And then with the spin-Hall effect and vertical injection, we have very large velocity for small current density, very small current density compared to what is needed with generally for domain walls. In fact, the first motion is a little with a transverse component, and then there is a repulsion by the edge expected, and there is this. What can be said? Of course, this the direction of this spin accumulation of the spin currents rotates with follows the direction of the current. So this motion can be propagated in structure, very complex structure with many zigzags. And also, what can be seen is that this can be simulated also with train of skyrmions, simulating some train of information, and we have the same large velocity for train of skyrmions. In fact, simulation have been obtained with the value of alpha for cobalt relatively large, and the velocity up to thousands meter per second can be obtained with material with smaller alpha probably. So in fact, this sort of simulations, Naigawa in Japan made the simulation only for in-plane current, so we extend the simulation to vertical current and spin-Hall effect. And we looked also to the problem of pinning. So again, a simulation with an obstacle, which is repulsing the skyrmion here. And you can see that what is the origin of the small pinning is the flexibility of the trajectory and even the flexibility of the shape of the skyrmion. So these are very flexible objects that avoid many obstacles and defects, and explain that the pinning is very small. This one is pinned, this one no. And in fact, the border between the two regimes can be seen in this picture. You can see this is blocked and non-pinned, and you can see as a function of the depth of the notch here. And you can see for typical roughness of the track, that is a few nanometers, you can see the deepening current is very, very small. It's much smaller than the deepening current for domain walls. So a few remarks on the applications, possibility of applications. Of course, for example, this is a typical example of MRAM based on the deflection of the motion of a domain walls in the bottom electrode here. Of course, if could be done also by moving a skyrmion, and of course with some advantage in terms of current density and energy consumption, and of course for the application of restrict memory, of the type of restrict memory. The system that Parking 1-2 develops is a system where with the information is there is no mechanical part, but there is also a motion of domains in a track. And of course, this could be imagined also developed with skyrmions with some advantage in terms of current density and low energy consumption. So it was to, I suppose I can have 10 minutes.
Whatever you want.
Okay.
But we have coffee also.
Okay. Okay, so I proceed to the second part of the talk, but because the second part of the talk is, you say, but there is so many things now to say on skyrmions that have been long on skyrmions. But second part, I put this part of the end because you see, I will anyhow speak about. If I speak a Rashba, electron effect, topological insulator, I know that we will be strongly interested, and so I could be a little longer on this part. Okay, so the second category of spin orbit effect: spinol, Rashba, delta, and other things. So spinol effect, we have seen already this example of a skew scattering. This is one of the mechanisms of the spinol effect that I've already described for skyrmions in metals with large spin-orbit coupling like platinum, iridium, deflections, and so this spin accumulation on the top of the film can diffuse a spin current into a magnetic material, and we have seen that can be used for skyrmions, and this sort of mechanism is supposed to work also, is used also in some MRAMs to reverse the magnetization for the same mechanism, not a skyrmion but a magnetization. The spin transfer torque related to this vertical spin ejection are well known. This is this anti-damping torque. There is also a term of smaller amplitude and different symmetry, which is a field-like torque, but mainly the main torque is the one that we have seen already in action for the skyrmions, sigma being the polarization, m the local magnetization. Okay, what is characteristic of this effect is the spinol angle, that is the ratio between the horizontal charge current density and the vertical spin current density that can be in some sample, in some material with large spin can be relatively large. You see 30% for tungsten here, or 44% for copper doped with bismuth, using the skew scattering by bismuth. Bismuth has a strong spin-orbit coupling. So this is a spinol effect is well known, and we know all these coefficients and the effect in several experimental situations. In fact, the spinol effect that described here is a conversion from charge current to spin currents. And there is also the inverse spin current, the inverse spinol effect, conversion from spin current to charge current. In fact, if one injects this vertical spin current, it gives rise to an horizontal charge current. Rashba effect. You know, the Rashba effect is result from the spin-orbit coupling for interface states. For example, between bismuth and silver, which has a larger alpha coefficient that has been measured. What is this Rashba interaction? Is this coupling between spin and momentum, again a spin-orbit effect related to the spin orbit of bismuth and to the strong and to the absence of inversion symmetry. And this interaction makes that these two spin orientation for this value of k, this direction of k, are different energy. And this difference is reversed when k is the opposite direction. And we probably know what this gives for the dispersion curve. For example, for quadratic dispersion curves, this gives this splitting between up and down on this side of k, and with the opposite splitting on the other side. So this sort of splitting of the dispersion curves, and if you cut at some energy, Fermi energy, you have in this two-dimensional electron gas, two Fermi contours, and the ground states of the system on these contours are spins, which is indicated by this arrow, and with, of course, different orientation, clockwise, anti-clockwise, for the small one and the large one. Okay, so Edelstein effect, and so the topological insulator is more or less the same thing, except that for topological insulator, this small contour disappears, and there is only the large one. So there is the maximum, the extreme limit of the hash bar coefficient, 100% hash bar splitting. So Edelstein effect. So I will Edelstein effect. If you suppose a charge current is flowing in the electron current is going in the two-dimensional electron gas, that means that the Fermi contour is shifted to the right here. And so by shifting to the right, what is even clear, that means that you populate additional effect with this spin direction, and the states that you depopulate add the opposite direction. So you are creating a non-zero spin density. This is the Edelstein effect. And of course, the effect is opposite for the second contour, as you can see, but of course there is only a partial compensation and something subsists. So the result, a charge currents induce a non-zero spin density. No spin currents, non-zero spin density. There are additional effects that I do not describe. The inverse is you inject a spin current. Injecting a spin current means injecting spin up this spin direction and extracting the opposite spin direction. That is, you inject spin direction electron on this side, and you extract electron from this side. And this is exactly what, for example, here you inject on this side. And in fact, what you do by this way, you create a charge current. Injection of spin current induced current. This is summarized in the next. A lateral charge currents induce a non-zero spin density that can exert, in some experiment, a field torque on an adjacent magnetic layer, or can also generate a vertical spin current diffusing in the other layer. And the inverse is injecting a spin currents induce a lateral charge current, conversion from spin to charge. I show you an experiment of this type. I suppose, at least for metal, this is the first example of experimental results. In fact, had been obtained in the group of Laurent Villa, which is somewhere here. I don't know where is he. In fact, experiment of spin pumping. So a silver bismuth bilayer, so with a typical hash bar interface, and permalloy with FMR to pump. This is a classical method to pump a spin currents into this. So this is the experiments. So this is an experimental setup. So spin pumping, resonance, injecting into this two-dimensional electron gas a spin currents, and look if there is a charge current detected by the voltage needed to annihilate the charge currents, to compensate the charge currents. Results, so the results, if there is only silver, nothing, no V equals 0, no charge current here. In fact, this is a charge calculated when one knows the lateral resistance. It's not surprising, silver has a small spinel effect. When there is only bismuth, a small signal, but then when there is at the same time silver and bismuth, if there is a typical hash bar silver bismuth interface, there is a large current here. Actually, there are also new experiments. In fact, this experiment, the sample were coming from Saragossa, from José María de Teresa, and now there is a co-worker of de Teresa who did the experiments now by reversing, that is, bismuth above silver instead of bismuth below silver, and the effect is reversed. I have now the experimental curve, but there is also a test of the mechanism that has been obtained by Soraya Sangayo recently, with a postdoc in France today. The result is that we have this, in fact, this does not depend on the silver layer. It's typical, it does not exist with silver only. This is a current here, current density by amp by the current divided by the width, two-dimensional systems. And so it can be, the result can be characterized by this coefficient characteristic of the interface, which is the ratio between the resulting two-dimensional charge current, amps per meter square, by the three-dimensional spin current, amps per meter square, this time, this perimeter, and this is a length. The characteristic is not like for spinel effect, a coefficient is length, and this is a length for several samples. We found always this typical length. That can be predicted by theory using this picture. It's possible to derive the spin current, charge current induced by some injection of spin currents, and one find this relation between this lambda and the Rashba coefficient. This is the Rashba coefficient, and tau s is the relaxation time of this out of equilibrium polarization. There is no momentum relaxation and spin relaxation and momentum relaxation in this structure cannot be separate. There is only a single time that we call tau s. Okay, so and the theory, a little more complex theory has been developed recently by Vignal and co-worker, Raimondi and co-worker, not in this picture of strong spin-orbit coupling, but in the picture with small spin-orbit coupling, and they have more or less the same expression. Of course, so it seems that we have an interesting experiment to probe the conversion between spin and charge by this type of two-dimensional system with large spin-orbit coupling. And of course, what we are doing now is the extension of the technique to topological insulator. Of course, the same theory can be developed for topological insulator, simply replacing alpha over h bar by the Fermi velocity of the Dirac cones. And so this is the extension of this sort of model to topological insulator is what we are doing on several types of topological insulator. And we have also similar results, not completely analyzed, but really very promising on the two-dimensional gas at the interface between these two classical insulating oxide, LaOSTO. Okay, so it was I developed a little this two categories of spin-orbit effect, spinel effect and Rashba-Edelstein. And so to conclude with one application of this effect is, in fact, there was a debate. In fact, people during the last year have remarked that the velocity of domain 1 can be very large when there are the film are deposited on materials with large spin-orbit coupling, platinum typically, or tantalum or tungsten. And and there was a debate, a violent debate sometimes between people saying, okay, this is a spinel effect, others saying this is a Rashba effect. And so both are possible. In principle, both are possible. So you can have spinel effect, injection of a vertical current, and mainly this torque, maybe a smaller one. And Rashba effect is expected to be the main torque is of the field-like form, symmetry. And there is also, in some approximation, also so both symmetry are possible, but this one is the predominant one probably with spinel effect, and this one. And so, in fact, there was a debate, but the conclusion we'll see is that the DMI has some role to play also in the problem. We'll see that the DMI also is essential to understand these experimental results. Well, in fact, we started to study this field a few years ago by trying to see what was the best symmetry to induce by spin orbit a domain walls. And we tried several types of domain walls, and in particular magnetization block and NEL. And so with the current along the magnetic track or perpendicular to the magnetic track, and using the expression of the spinel effect or Rashba effect, these two types of torques, where, say, I repeat, sigma is the direction of the polarization of the currents, yeah, this one, perpendicular to the current, yeah, and M is the local magnetization, okay, sigma and M, sigma is, okay. And so, in fact, the results were puzzling, okay, there was presented this is the total result. We consider only the situation parallel, that is situation, this one. And so the result was puzzling. Okay, we see the only situation with steady motion where the spin orbit acts normally is for the anti-damping torque, tau parallel, spinel effect. But with the puzzling result for Néel walls, and Néel walls is something very unstable. It cannot exist generally except in very narrow ribbons. And also one knows that it can be destroyed by any motion. This is a Walker breakdown. And also the other puzzling result, we found that for different chirality of the Néel wall, the velocity was in opposite direction. So there was a puzzling problem. And this problem can be solved by the existence of DMI. And so this is this paper. And where when used by spinel effect in a domain wall with a given chirality induced by the DMI as a function of the magnitude of the DMI. Okay? And you can see that, of course, with a small DMI, the domain wall, the velocity is very small. The domain wall is immediately transformed into a block wall. And then, but increasing progressively the DMI, it stabilizes strongly the structure of this right-handed normal wall in this case, and allows the system to propagate with a large velocity. So this was the result that, in fact, it's possible to combine two spinel effects, DMI to stabilize the structure with a given chirality, of course, with always the same direction, because we induce, DMI select one of the chirality. And this effect has been confirmed by several publications now, especially the publication by the group of Beach at MIT, but also some other ones. And so, for example, this is one of the first publications by Beach and co-worker. It's for cobalt, iron, and platinum or tantalum, and heavy metal, and the DMI stabilized chiral domain wall whose spin texture enable extremely efficient current driving motions. And in fact, there are several clear signatures. For example, if in addition to the DMI stabilizing, for example, this left-handed rotation, you add a longitudinal field, you will stabilize the domain wall if it is in this direction, or destabilize if it is in the opposite direction, is what you see here. Adding this longitudinal field can stabilize more or destabilize and lower the velocity and the difference for another type of domain walls. So in fact, this is a good example of first of the similarity of the problem of skyrmions and domain walls, and also to an example of experiment in which it's possible to combine several effects, spin-orbit effect, DMI, and spinel effect to do something. And so it's not surprising that the best situation is chiral domain walls and skyrmion, because in fact, what is a skyrmion is along this line is a double domain wall similar to this situation. So this is to come back to the beginning and to the skyrmions. This is an example of the similarity of of the similarity between these spin-orbit effects in the field of domain walls and for skyrmions. Okay, so I will. I suppose I have two slides on graphene, but okay. Even there was a figure from your paper, but okay, people know this also. And so, okay. And so we say there is next, there are several things to do in this field. The next step will be topological insulators, more difficult experimentally, and graphene, referred to a recent paper by Pedro on graphene, and you certainly, you are on this paper. And other two-dimensional material, MOS2, etc. And the last transparency to thank my co-worker, the group working with me at this laboratory, joint lab of the CNRS and company Thales, with an association with Université Paris Sud. And the simulation of domain walls are being performed by Alexei Kalkowski, who was with us. Now he's not at San, so he came back to Moscow now. The simulation of schema melee by Jayo Sampaio in collaboration with Thiaville and Roa, and now with his students and Nicolas Reren, and the work on spin pumping and Edelstein effect by Laurent Villa, which was somewhere in the room here. And in Grenoble, you can see this typical landscape of Grenoble, and a postdoc was Juan Carlos Rojas Sanchez. And I thank you for attention.
Okay, now we have about time for 3 or 4 questions.
Yeah.
Then we have informal coffee, so you all can discuss and talk with him. And in any case, he will be here until 12:15 for the ones who want to talk to him informally. So now, questions, please.
Let us assume that we start at the very beginning.
Well, let's wait a second for the microphone.
I want to start beginning from Sasha Belavin and Sasha Polyakov paper.
So,
Sasha Belavin and Sasha Polyakov paper, in which they introduce the skyrmion.
yeah.
Skyrmions.
Yeah.
So long ago. And they are in unstable state, or in marginal, or in meta-stable state, due to the scale transformation. Let us assume that we have a set of perturbation. Who is the main participant in this set? Can I understand that the main perturbation is due to the Zelashinsky-Maria interaction? Is it correct?
Yeah. The Dielashinsky
Is the main.
Is the main.
Yeah.
Is the main term.
Yeah, because this term is the gradient, proportional to the gradient of speed.
Yeah, the
Instead of
Dielashinsky
the
Maria is a
gradient
gradient.
squared.
Yeah. Yeah, this is a term that makes that the spin cannot be parallel but try to rotate clockwise or anti-clockwise.
But because the Belavin Polyakov term is proportional to the gradient squared,
Yeah.
and Maria is squared in the power 1,
Yeah.
therefore is the main.
Yeah, okay. So no, this is all the simulation are, and the general idea now is that the Dielashinsky Maria, it works with the first order term, Dielashinsky.
Yeah.
In these domain walls, you can say that clockwise, anti-clockwise, opposite effects by tested by some field, longitudinal field. So this is the first order term that is in action.
Yeah. Thanks.
When you combine spin or ferromagnetic material and Rashba-like metal,
Yeah.
what could be better if instead of Rashba-like metal you could use semiconductor with strong Rashba or Bachkov-Rashba spin-orbit splitting? In the case of semiconductor, you can organize the so-called surface state, which is located inside the energy gap of fundamental energy gap. So it means no any scattering of this Rashba split state on bulk electrons. In the case of metallic systems like bismuth on silver, you have local energy gaps. And of course you have scattering, and what could be more efficient, combining ferromagnetic and strong Rashba split surface state in semiconductors, or
it's better. Okay, instead of having, if you have metals, you have this problem of diffusion into the metal, into the conductor. The best situation will be a Rashba gas between an insulating magnetic material and an insulating substrate. What you mean? No.
Okay.
Yeah.
I mean, instead of using metallic Rashba-like system, because metallic means bismuth.
You mean semiconductors. You mean semiconductor.
Exactly.
But I would say
with Rashba surface state splits.
Yeah, even better, I would say two insulator, one magnetic and two insulator
Okay.
with
Both semiconductors.
yeah, or both
Okay.
semiconductors or both insulating. For example, a good systems is certainly LaO-STO, these two oxides. Of course, to concentrate also the current in only in the two-dimensional electron gas. In terms of application too, in terms of energy, if you have the currents spreading into several layers of small resistance, finally the total power that you can recuperate is RI square. And you need to have the larger resistance to have the maximum power. I consider my language is a language of application.
We'll discuss.
Sebastián, Andrea?
Regarding the size of the skyrmions,
Yeah.
there is some kind of lower bound for the
Lower bound, I will say that when in the smallest one, those of Wiesendanger for 1 molar, the diameter is 1 nanometer and the system become complex because now we are an interference between the atomic distance is only a few atomic distance. So, okay, there is this example, this extreme example. I don't think for my point of view for application is too small. Huh? It's much too small.
What was the 1 nanometer?
Yeah, 1 nanometer. So anyhow, I am not only, it's complex, it becomes complex because now there you cannot use, for example, micromagnetic simulations, of course. And so one goes into a very complex problem and also not interesting for application. They are too small, they are never stable at room temperature and so on.
In the simulation that you showed where you generated the skyrmion, if I saw this correctly, the contact with the spin polarized current is actually half the diameter of the disk.
Yeah, of the disk, yeah.
I'm sure you did this for a reason. What happens if it's the diameter of the disk?
To try to, we try to reverse not all the disk, because if you send the current in all the disk, we will reverse the total magnetization. We wanted to reverse the center and create a bubble in the center, and then this bubble evolves to, at some time, becomes to become a skyrmion. Okay.
But did you play with the diameter that you use? And
we play sometime, yeah, but not really, never injecting in the total area of the disk.
Thank you.
Nacho? No? Nacho, you want it? No. Yes, please.
About the mobility of the skyrmions,
Yeah.
you show that you can modify, put in notches. What about impurities, magnetic or non-magnetic impurities? How is...
Yeah, the simulation with, our simulation are with defects. Simulation with impurity have been performed by Nagaosa in Japan. And so, so they can go around the impurity and so on. Okay, so, and sometimes they can be attracted also by impurity. But generally, the pinning is always very small. But you can play also by, I saw recently some simulation in Cologne, where they try to see if they can pin some skyrmion by impurity. Okay, there are some games can be done with impurity.
But in general, the mobility is better compared to domain walls or
Yeah, no,
vortices.
the mobility, the pinning is very small. The pinning is very small, but you can, in some condition, try to enhance this pinning to do something. Yeah?
Okay, there is no more questions. Thank you very much for this.